now we're at the point in the story where we finally get to introduce one of the great, amazing, wonderful heroes. We get to introduce Isaac Newton. If I was to pick the 3 most important human beings who have lived in the last 1,000 years, Isaac Newton would be one of them. I'd also have to go with Johannes Gutenberg, who invented the printing press. You don't get anywhere without the ability to publish books and stuff like that. I'd also go probably with Louis Pasteur and that whole germ theory of medicine, which turned out to be very useful as well. But Isaac Newton is huge. He is the scientific revolution. He puts it all together, he consolidates it, he puts it in one big package that just amazes the whole world and permanently and forever changes everything, convincing everybody that, you know what? Science works. So here's where we are, just to recap. We started out in ancient Greece, where people are studying the motion of the planets. So we're doing motion of the planets. Not the nightly motion in the terms of one night. Well, planets rise in the east and set in the west just like everything else does, except for circumpolar things, and planets aren't circumpolar. So things rise in the east and set in the west. But no, what I'm doing is I'm looking at the position of Jupiter with respect to the constellation Taurus, and I'm comparing it to night, and a week from now, and a week from after that, and a week from after that. And when I do that, okay, so what does Taurus look like? There's the Pleiades, here's Jupiter, there's tonight, and a week from now, and a week after that, and it moves with respect to these stars, and then sometimes it turns around and moves backward, moves retrograde, sometimes then turns around and moves forward, and goes like this. And so we see this pattern of motion when we compare where Jupiter is with respect to the stars tonight, and the day after that, and a week after that, and 2 weeks after that, and 3 weeks after that, and we see it moving forward and backward. It slows up and speeds up, it changes speed, it stops, it changes direction, it moves backward, it moves retrograde, sometimes it gets brighter. It's complicated. It's interesting. It's fascinating. All right, then, so what do the Greeks do? And the Greeks had lots of ideas, but the one that all ultimately held sway, the big giant model, was the model of Claudius Ptolemy. Claudius Ptolemy put the Earth right smack dab at the center and said, all right, all the planets move in perfect circles around the Earth, and then in their big, deferent, perfect circles around the Earth, they move in these little epicycles around that. They're moving at constant speeds on both circles, going loop-the-loop sort of patterns, and this could then be used to predict, well, where is Jupiter going to be in August or June or February, or wherever you want to do. Using this, Claudius Ptolemy worked out the exact sizes of all the circles, both the deferent circles and the epicycles, and the exact speeds of the epicycles and the exact speeds of the deferents for all of the planets as they moved in their orbits around the Earth. And using that, people were then able to predict with decent accuracy exactly where the planets would be when they go in retrograde. It seemed wonderful, it seemed glorious, it seemed fantastic. It worked for hundreds of years until people realized it was off. And so they tried to tweak it and fix it, and no matter what they did, they couldn't get the geocentric, Earth-centered epicycles on deference models to work. They tried everything, they tweaked this speed, that speed, all that sort of thing. So finally, we got motion of the planets, we got Claudius Ptolemy, and his geocentric model. So 1,000 years or more after Ptolemy, then you get Nicholas Copernicus. And Copernicus says, no, we've got it all wrong. The basic assumption of Ptolemy's model is wrong. Things aren't moving in circles around the Earth, they're moving in circles around the sun, and the Earth moves too. And so he comes up with his models. He figures out the exact size of the orbits of all the planets around the sun, the exact speeds in their orbits. People try it out. There's a variety of philosophical issues, but ultimately it fails because it doesn't predict the positions of the planets in the sky any better than Ptolemy did. It's a great approximation, gets you pretty close, but it's off by a few days here and there. It doesn't quite do it. So people go back to the drawing board. After Copernicus, you got Tycho Brahe, who says, okay, his main contribution is gathering lots of data. He did tons of stuff. But the main thing is, okay, we need more facts in the table. Let's observe the exact precise position of the planets in the sky every night for years on end. And then he's going to work out things, figure it out. He tries and tries and tries, and then dies. Okay, then the next person on it is we've got Johannes Kepler. He solves the mystery of the motion of the planets. He comes up with a model which really does accurately and precisely predict where all the planets are in the sky every night forever. His model works beautifully. It's glorious. It's right. Except that it's weird. Now, the mystery changes. Before the mystery is, well, why did the planets why did they do this? Well, now the answer is Kepler's 3 laws. Kepler's 3 laws. Number 1, planets move in ellipses, not circles, in ellipses around the sun. Ellipses. And what is an ellipse? Well, it's this kind of squashed shape. It has two focus points. The sun's at one, the other's empty space, and okay, interesting. And then planets move faster when near the sun, which kind of makes sense, but why? And he figures out exactly mathematically how much faster when near the sun, how much slower when far from the sun. Then finally he finds that p squared, Kepler's third law, p squared equals a cubed, where p is the period of time it takes each planet to orbit the sun, and a is the distance of each planet from the sun, and p is measured in years. A is measured in AU, and he finds if you take this number and square it for every planet, then it's equal to this number cubed for that planet. So if I take, the period of time it takes Jupiter takes 12 years to orbit the sun. So I take 12 and I square it, and I take Jupiter's distance from the sun in AU and I cube it. These are equal to the same number. And so now we understand why the planets orbit the sun, except we don't understand why the planets orbit the sun. Why do they follow Kepler's three laws? I mean, okay, if they move in circles, Copernicus's model has a simplicity to it, at least. They're okay, they move in circles. What's a circle? Is simplest. A circle is one of the simplest possible shapes. An ellipse is not. It's a slightly more complex shape. So why do they follow Kepler's three laws? How come they move in ellipses? Why is the sun at one focus and nothing at the other? Why is the period of time for an orbit squared equal to the orbital distance from the sun cubed? What's the story on that? Why? Why do the planets orbit in ways that follow these laws? And to explain these strange, bizarre, interesting mathematical patterns, that's Isaac Newton. So, Isaac Newton's living in the 1600s. You remember Kepler's publishing his stuff way back in the early days of the 1600s. Isaac Newton's born on Christmas Day. And he's a fascinating character. He's born in Woolsthorpe, England. He's born in Woolsthorpe, England. And he's nobody. He's almost a peasant. He's born to a family without any money. While his mother was pregnant with him, his father died. And so at very young age, he doesn't have a father. And then when he's a few years old, his mother married another guy, found it kind of inconvenient to have this Isaac little boy running around. So she ships him off to his grandparents, and he's mostly raised by his grandparents. And so he grows up there, and then when he's about, 15, 16, his mother said, well, our family has these farms. He's going to be a farmer. Send Isaac back, and we'll teach him how to be a farmer. And that's going to be Isaac Newton's life. Except that, he was doing rather good at school, doing rather well at school. So his teacher and pastor and stuff had some thoughts about this and suggested, hey, he should go to university. Now, in England at this time, there weren't a ton of universities, but there was Cambridge. Oxford as well, a couple other sorts of things going on. But he ends up going to Cambridge. But he's nobody. He's not a lord. He's not a baron. He's not a gentleman of any sort. He's going to be trained to be a farmer, for crying out loud. But he ends up going to Cambridge just because he's really good at math, And so they ship him off to this, and he doesn't have the money to pay for it. At this point, Cambridge is mostly for the sons of great lords to meet each other and hang out and drink beer together and pretend to study Aristotle during their days. So he's there. He has no money. So how does he pay for it? Well, he's given the job basically as a janitor. He cleans rooms. He cleans the mud off of the other students' boots and stuff like this. So he's looked down on a lot. He gets there, and what are they studying? They're mostly studying Aristotle. They're mostly studying ancient Greece stuff. None of this, this Galileo stuff, the Kepler stuff, all the cool stuff that's going on is not part of the university education in those days. So he finds the studies boring. He finds the tests trivial. He becomes famous for not attending any of the lectures. He just shows up for the final exam, and then he aces them because the tests are all about, just ancient documents, and it's some logic and stuff. And it's basically designed so that the sons of lords can get nice degrees before they go off and rule over the peasants. Isaac Newton doesn't fade into that category, but really fortunately, he happens to bump into a professor there whose name was Isaac Barrows, who was involved in the interesting stuff going on, who was involved in the early embryonic ideas of calculus which were going on, who was aware of this. I don't think he taught any courses that Isaac Newton actually took, but they got to be friends. And he talked to him, and he gave him all the right books. And Isaac Newton became aware of the Kepler problem. Why do the planets orbit in ellipses around the sun? Why do they do this? And Isaac Newton gets interested in this, and he starts studying this, and he gets interested in this, and he's in Cambridge, and he's spending lots of time on all sorts of things. He had all kinds of crazy interests. I mean, Isaac Newton is a very eccentric character. He spent a lot of time in alchemy. He spent a lot of time looking for codes in the Bible. He was a deeply, deeply religious man, much like Kepler and Galileo and Copernicus. I mean, Isaac Newton was really serious. But one thing he got interested in is the Kepler problem, and why would the planets orbit in ellipses around the sun? So he's working on, all this sort of thing he gets interested in, and then what happens? Well, the plague comes through. And we don't have plagues anymore. Thank you, medicine. But here's what happens. When the plague comes through, this big, horrible, come through in 1666, this horrible plague comes through England, so they dismiss the school. They say, all right, everybody go away. We know that if, they don't know they don't know anything about germs or anything like that, but they do know if you're around people who are sick, you might get sick too. So let's dismiss school, go home for a couple of years, don't go to London town. There's all kinds of people who might make you sick there. So no, go home, hang out for a couple of years, and then come back if you're still alive in a couple of years, and we'll start up Cambridge again. So this is what happens. And so, I mean, this is the plague. We have that children's nursery rhyme based on this plague. Ever hear Ring Around the Rosie, Pocket Full of Posy? That's the plague of 1666 they're talking about. The first symptom of the plague is a rash around the nipple. There's the ring around the rosy. And when people got that, there was a superstition if you carried around, the right herbs and plants in your pocket, that might make you better. Pocket full of posy. The next thing is once you started to sneeze, a tissue. Once you start to sneeze, you had 24 hours before all fall down. Anyway, so tons of people die. Fortunately, Isaac Newton didn't. He went out to the family farm sort of thing out there where they had all these big giant apple orchards. Maybe you've heard of that. And they kind of left him alone. They knew he wasn't going to be a farmer. He's doing well in school, and he plays on things, and he works with things, and he makes all kinds of amazing, extraordinary discoveries. But the thing he ultimately focuses on, that does it, is he figures out how to explain the way the planets move in orbits around the sun. He figures, his great leap of logic is that, hey, maybe the force which makes apples fall from the tree is the same force that holds the moon in its orbit around the sun. According to Aristotle and people like that, they knew that gravity existed, but gravity is the force that pulls objects to the earth. And up in the heavens, well, there are totally different forces. And Newton says, no. Every object in the universe has gravity. I have gravity. You have gravity. The Earth has gravity. It's what holds the moon in its orbit. The sun has gravity. That's what holds the planets in their orbits. Jupiter has gravity. That's what holds Jupiter's moons in orbit around Jupiter. Saturn has gravity. Everything has gravity. My left hand and my right hand have gravity. They are right now gravitationally attracting each other. The force is tiny because their masses are small, but that exists. So Newton says everything has gravity. He proposes a mathematical law for gravity to follow. He works out the laws of motion based on the work of Galileo, and along the way he discovers that the mathematics of the time isn't advanced enough to work out the orbits of the planets. So, oh yeah, he also invents calculus. So, he works out all the details of this, explains why, the force of gravity varies inversely square with the distance, and using calculus he can show that this is why the planets orbit in ellipses, and why they move faster when they're near the sun, and why p squared equals a cubed, why Kepler's third law works. And he works all this out and thinks, oh, that's interesting, and then puts it in a desk drawer and forgets about it for several years. He comes back to Cambridge, he shows just teensy little bits of this to his teacher Isaac Barrows, who's actually moving on, and says, hire Isaac Newton. So Isaac Newton gets Isaac Barrows' old job. Newton's a horrible teacher. He's an awful lecturer. He's a disaster in the classroom, but he's a great scientist. And so eventually Edmund Halley is coming from London, asks him about some things, and he says, oh yeah, I figured that out years ago, the Kepler problem, I solved it. And Halley's like, could you tell us about that? And he's like, oh sure. He's lost the papers. He reworks it. He shows it to Halley. He writes a work. He writes his work called the Principia. Newton's Principia Mathematica Philosophia Naturalis. He writes it in Latin. He's Newton's old school, man. He writes his work and it changes everything. It changes the world. With that work, he shows how these laws of motion really do explain the motion of the planets and calculus and all sorts of geometry and wonderful things along the way. And it changes the way everybody thinks about everything.